let's take a brief look at exponents before we get into talking about scientific notation. An exponent is seen as a number written above, in this case a variable, could be written above a number, 3 squared, say. And what that means is we want to multiply this number here, the base, that's called the base. We want to multiply it by itself that number of times, and that number is called an exponent. So this is telling us 3 times 3. So 3 squared is 3 times 3, which is 9. Now in an expression like we have above, this is called a polynomial. We'll get into that a little bit later. But what makes it a polynomial is that it's made up of terms. And it's the exponents on the variables that decide what's a term as distinct from another term. For instance, both a squared and 3a have an a, but this one says a times a, and this one says a times 3. So these two are not like terms. Like terms have the same variable or variables and the same exponents of the variables. So for instance, a squared times a squared, those are like terms. That would be, well, let's say a squared plus a squared. Those are like terms, and that would be 2a squared. Another thing I want to take a look at is this constant number 1. See, it doesn't look like it has a variable, but there's a definition that I'd like you to keep in mind, that any number to the 0 power is 1. So this 1 here is like saying a to the 0 power. So it's a squared plus 3a's plus a to the 0 power. And that might not sound interesting at the moment, but you'll see why that becomes important a little bit later. Basically, this is in descending order. But let's take a moment and talk about these exponents. How do I deal with exponents? What if I'm multiplying exponents? And those exponents, the bases are the same, but the exponents are different. Now what I'm going to do is I'm going to expand this and show you what it looks like. And you're going to have to tell me what the rule is. You can put it in the comments below, or I'll give you, in class, I'll give you a method for explaining to me the rule that you come up with. So I have here a to the 3rd power times a squared. Well, a to the 3rd power is the same thing as saying a times a times a. And I'm going to multiply that by the quantity a times a. So what I have now is 1, 2, how many times am I multiplying a by itself? 1, 2, 3, 4, 5. So a to the 3rd power times a to the 2nd power is the same thing as saying a to the 5th power. Let's see that work on another number. Let's say 2 squared times 2 to the 3rd power. Well, 2 times 2 is 4, and 2 times 2 is 4, times 2 again is 8, and 4 times 8 is 32. Isn't that the same thing as 2 to the 5th power? If you don't believe me, take out your calculator, type the number 2, and then hit the X to the Y button, and then type the number 5 and see what it gets. You'll get 32. So what is a rule for knowing that x to the 5th power times x to the 7th power is x to the 12th power? How do I know that? I don't want to write x 5 times and then 7 times. Just tell me how I would know that. This is what we're going to call, since we're multiplying, this we're going to call the product rule of exponents. I'll take another color. Whoa. I'll take another color, and we will do the quotient rule of exponents. And let's see what the quotient rule looks like. The quotient rule says if I have a to, let's say, the 5th power, and I'm going to divide that by the same number raised to, say, the 2nd power, then what I essentially have is on the top I have a times a times a times a times a. And on the bottom, in the denominator, I have a times a. So if I have a to the 5th on the top and a to the 2nd power in the denominator, don't I have a couple of examples of a 1 here and another? Let's do this in a different color. That wasn't terribly successful, but I have a 1 here, I have a 1 there, and I have a 1 there. So those pretty much can go away. I now only have the a's on the top, and that's a to the 1, 2, 3 power. And it works the other way too. If I have x to the 4th power up here and x to the 8th power down here, well then in essence don't I have 1, 2, 3, 4 up there, and 1, 2, 3, 4, 5, 6, 7, 8 here. And those will cancel with those will cancel, those will cancel, and those cancel. And I'm left with just these on the bottom here. So that's 1 over, because these cancel to 1, that's 1 over x to the 4th power. Now generalize that rule for me. Up here I'm asking you to generalize the rule a to the m power times a to the n power equals a to what power? Give me the generalized rule there. And so I would like the same here. I would like for you to give me the generalized rule. A to the m power divided by a to the n power is a to the what power here. Well, so far we've looked at the product rule for exponents. We've looked at the quotient rule for exponents. So let's see what happens when I raise an exponent and exponent. Oh boy. Let's see what happens when I raise an exponent to power. Let's say I have 2 to the 3rd power and I'm raising it to the 2nd power. Well, in essence what I have there is 2 times 2 times 2 twice. So a grand total how many 2's here? 1, 2, 3, 4, 5, 6. That would be 2 to the 6th power. And that works out, right? 2 times 2, that's 8. Times 2 times 2 times 2 is 8, and that's 64. And if we knew from earlier that 2 to the 5th power is 32, then if I multiply 32 by 2, I'll get 2 to the 6th power. That's 64. So everything checks out there. So again, you tell me what the rule is. If I'm raising, let's generalize this rule. If I'm raising a number, a, to a power, m, and I take that whole thing and I raise it to the nth power, what will that be? How would I acknowledge that that's a to the what power? right? A to the question mark power. You tell me how that works. And how is that affected if the number were a fraction? What if I had a to the m power over b to the n power, and I raise that to the q power? What happens to my a and to my b in this case? You generalize that rule for me.